Nearly 100 elements have been discovered and their properties systematically organized in the periodic table of the elements. In Part 2, we will take a fascinating tour of some of the essentials of chemistry. Along with the newly organized periodic table, a whole new understanding of the atom emerged, and with it, 3 new atomic players: neutrons, isotopes, and ions. What do we know about atoms so far? We know there are positively charged protons in the center, the nucleus, and as a proton is added, the positive charge is 1 greater and instantly changes into the next element on the chart. Amazing. Therefore, the positive proton count for any element must always remain the same. That proton count is known as the proton number, or the atom's number, the atomic number. We also know the positive protons are surrounded by enough negatively charged electrons to keep the atom electrically balanced, or neutral. Lithium has 3 protons and 3 electrons. Now, a proton weighs just one atom unit, pretty small stuff. And electrons weigh next to nothing. In fact, it takes 2,000 electrons to equal the weight of just 1 proton. And there is no element that has even 200 electrons, let alone 2,000. Even uranium, the heaviest natural element, has only 92. All the weight, the stuff of an atom, is packed into the nucleus. But for years, science knew that the atom weighed too much. The nucleus of an atom weighs more than the sum of all its protons. Something else that's heavy must be lurking inside the atom. And in the 1932 issue of Nature magazine, James Chadwick published what that something was. With the assistance of none other than Sir Ernest Rutherford, who else, James Chadwick found that there was another heavy particle sitting inside the nucleus, weighing slightly more than a positive proton. They called it the neutron, as it was neutral. It has no electrical charge, which is why it was so difficult to find. No magnetic field to disturb it or to discover it. Here was the missing weight. And this is why you will find another set of numbers on most periodic tables. Here is the atomic number, the proton number for helium, 2. 2 positive protons in the nucleus. And then there's this number, 4. This number is the total weight of the atom and is called, yes, the atomic weight number, or the atomic mass. Since there are 2 protons in there and the atomic mass is 4, this tells you that there must be 2 heavy neutrons in there next to the 2 heavy protons. Look over here at carbon. Carbon's atomic number is 6. 6 protons in the nucleus. And carbon's atomic weight? 12. There must be 6 heavy neutrons in there with the protons. Beryllium is atomic number 4. 4 positively charged protons in the nucleus, which makes the atom into beryllium. And the atom's weight is 9. So there must be 5 heavy neutrons lurking inside the nucleus, making up the additional weight along with the 4 protons, since 4 plus 5 is 9. As you look down the chart, the number of neutrons added must be immense. Look at mercury, atomic number 80. That's 80 positive protons in the nucleus. And the atomic mass? 200. There's 120 neutrons in a mercury atom. Although electrically neutral, neutrons are believed to exert a special force called the strong nuclear force that helps keep all these positive protons from flying apart in the nucleus. Sir James Chadwick received the Nobel Prize in Physics for his discovery of the neutrons. And why? because this particle does not need to overcome the repelling electrical force found in the nucleus, because it's neutral and it's heavy. As a result, an extra neutron can be forced into the nucleus of an atom, prying it apart and releasing tremendous energy when it splits. After Chadwick's neutron discovery, he later wrote, "I realized that a nuclear bomb was not only possible, it was inevitable. It was then that I started taking sleeping pills. It was the only remedy." Splitting atoms and releasing energy was at least one application of these heavy neutrons. But neutrons also led to the discovery of another part of the periodic table, isotopes. We've established that the atoms of a particular element all have the same number of protons, the atomic number, and that's what makes them each uniquely different. Add a proton, change the element. But what would happen if you added an extra neutron to the nucleus? Well, it turns out that there are actually varieties of each element, all depending on the number of those neutral neutrons. See, there's not just one kind of root beer, there's a variety of kinds of root beers. There's not just one cola, there's a variety of kinds of colas. And there's not just one kind of iron, there's a variety of iron. And there's not just one kind of carbon, there's a variety of carbon. Take hydrogen. Regular hydrogen has one proton, no neutrons, and one electron. What happens if we add a neutron in the nucleus? Well, the positive electrical charge remains the same, so it's still hydrogen, but the nucleus gets heavier by 1. Now the mass or weight of the hydrogen atom is no longer 1, but 2. It's still hydrogen, but it's heavier, and thus a little different. In fact, we can add a second neutron to the nucleus, and the weight will now be 3. Still hydrogen, but heavier hydrogen. Scientists call the heavier hydrogen deuterium, meaning second, and the very heavy hydrogen atom is tritium, meaning third. They also refer to them as hydrogen 1, 2, and 3. 3 slightly different versions of hydrogen, but all in an equal place on the periodic table, sort of stacked behind regular hydrogen, which is called hydrogen 1. Or take carbon as another example. Regular carbon has 6 protons and 6 neutrons. Thus, it is called carbon-12. 99% of all carbon has 6 neutrons and is carbon-12. But there is a carbon-13 and carbon-14 flavor, each with an extra neutron making it heavier. 3 different varieties of carbon, all in an equal place on the periodic table. And what is the Greek word for equal place? Isotope. Iso is Greek for equal, like an isosceles triangle is a triangle with at least 2 equal sides. An isotope is a variety of an element in the equal place. So, when you look at the face of the periodic table and the listed atomic weight, you are generally looking at the most stable or abundant form of the element. And stacked behind most elements in the equal place are the isotope versions of those elements. Same number of proton, but a different number of neutrons. Thousands have been artificially made in laboratories, but there are about 250 stable isotopes, almost quadrupling the number of element flavors to experiment with. In nature, some elements have only one stable isotope. For example, fluorine-19 is the only stable isotope of fluorine. Xenon has 9 stable isotopes, and tin has the most naturally stable isotopes with 10. But most isotopes are unstable. They are radioactive. They fall apart easily and begin to actively radiate particles, disintegrating into more stable elements. With the lightest elements on the periodic table, the number of protons and neutrons is about the same, half and half. But the heavier elements need more neutrons to keep all the positive protons from flying apart from each other. Notice that most atomic weights aren't whole numbers. They end in decimal points. That's because the atomic mass is the average weight of all the isotopes, including their natural abundance. See? Mercury has 80 protons and an average atomic weight of 200.6. So there's about 120 neutrons in an average mercury atom. Although there are 7 stable isotopes of mercury, that is, mercury 196, 198, 199, 200, 201, 202, and mercury 204, mercury 202 is the most abundant. Nearly 30% of all mercury atoms are mercury 202, with 122 neutrons. When the weight and the abundance is averaged out, we get a precise average atomic weight of 200.6 atomic weight units for mercury. So, simply speaking, an isotope is an element with the same number of protons, but a different number of neutrons. And by the way, we keep talking about mass and weight, and technically, mass and weight are not the same things, though for you and I here on Earth, they're just about identical. Mass is a measurement of the amount of matter or stuff in an object. Weight is a measurement of the gravity that pulls on that stuff. So, here on Earth, this rock weighs about 2.5 kilograms, or 6 pounds. But gravity on the Moon is 1/6 of what it is here on Earth. So on the Moon, this same rock weighs about 1 pound, or half a kilogram. Same rock, same stuff, same amount of mass. But gravity pulls harder here on Earth, and so the rock weighs more here on a scale. As you can see, these terms do not technically mean the same thing. But most experiments done in laboratories are done on this planet, and chemists use these terms interchangeably all the time without any confusion. And in Chemistry 101, we will do the same. Incidentally, the only way to actually weigh the mass of an object is to weigh it against the known weight of another object. And for over 100 years, everything in the world has been weighed against a specific standard. This standard, called the grand kilogram, or Le Grand K. It is a bar of platinum iridium made in 1880 and kept in a vault at the International Bureau of Weights and Measures near Paris, France. A kilogram is defined as the mass of this object. All kilograms on Earth are calibrated from the Grand K, including this one vaulted at the National Institute of Standards and Technology, and this one at Sandia National Laboratories. This piece of metal reigns over the world of weight. Every bag of rice, every postal letter, every gram of medicine, everything that is weighed in the world is ultimately gauged against this one object. High-precision experiments, including those measuring force, light, electricity, and pressure, are highly dependent on the never-changing stability of the Grand K. It is kept secured in a triple-sealed bell jar inside a temperature and humidity-controlled vault inside a secured room in this building in Servais, France. Very few people ever get anywhere near the Grand K. Nobody touches it. Nobody even breathes on it, as that would slightly change its mass. In fact, in over 100 years, the Grand K has only emerged from its protective vault 3 times. Most recently in 1990 for a formal worldwide verification of weights, and to their shock, the Grand K has changed. In 100 years, it has lost the equivalent weight of 1 grain of salt, or the same as having a stack of $100 million in pennies and finding that you've lost 30 cents. Not much, but enough. Suddenly, everything compared against the Grand K overnight became ever so slightly heavier and longer and faster. And the only thing that really changed was the Grand K. What could be done? This platinum iridium bar used to be the standard for the length of a meter, but in 1983, it was replaced by defining a meter as the distance light travels through space in 1/299,792,458ths of a second. The bar was replaced by something that wouldn't change even a tiny bit for a long, long, long time. The International Bureau of Weights and Measures continues to meet to find a replacement standard for the kilogram based on a similar constant in nature. But until then, all weights worldwide, all measurements of mass, will continue to depend on this piece of metal that is ever so slowly getting lighter and lighter. So, the number of protons in the atom remains constant and determines what the atom is. If you change the number of neutrons in the nucleus, it changes into a different variety of that element. Same element, same place, different variety, isotope. Now, what else is there in an atom we could toy with? Let's see, there's protons, there's neutrons, there's electrons. What about electrons? What happens if we change the number of electrons in an atom? Well, the element would certainly stay the same since we haven't changed the number of protons, but it would definitely affect the electrical balance, and the atom would no longer be electrically neutral. So, if you take away a negatively charged electron, the balance changes, leaving more positive protons, and the atom becomes positively charged. If an electron is added, there are more negative electrons than protons, and the atom is negatively charged. These electrically imbalanced atoms are known as ions. Michael Faraday actually coined the term from the Greek word meaning to go. Like in this battery, atoms go from the negative pole to the positive pole. To ionize something is to take away or to add electrons and electrically charge the atom. And that's the thing to remember about ions. They are electrically charged atoms. Massive amounts of electrically charged atoms, ions, build in thunderclouds and discharge as lightning. Moving water mists the air with negative ions that smells refreshing to us. Ions from the sun enter the atmosphere and are the cause of the northern lights, an electrical color show in the atmosphere. Ions are electrically charged atoms. You can ionize atoms using a comb just by rubbing it through your dry hair. Just like the ancients who would produce static electricity by rubbing fur and amber, the comb and your hair acquire opposite charges, and your hairs have the same charge, which is why on dry days your hair stands on end after you comb it. Each hair is positively charged, and they repel each other, just like a magnet. In fact, there's a chart called the triboelectric series that shows the static electric charge different materials produce when rubbed together. Hair picks up a positive charge, and plastic picks up a negative charge. Tribo, incidentally, is Greek for rubbing. Triboelectric, rubbing electricity. A trickle of water has free-flowing atoms, and if you place the negatively charged comb next to it, the positive particles in the water will be lightly attracted to the negative comb, bending the trickle slightly. A spoon or balloon rubbed against your clothes also works, especially if your clothes are made of nylon or acrylic. Incidentally, chemists call the atom with a negative charge, with too many electrons, anions. But positively charged ions they call cations, and yes, it's spelled just like it sounds, cation. And if you feel particularly positive about cats, this probably shouldn't be very difficult to remember. Cation, an atom with a positively shocking charge. Any element with a positive charge is a cation. With the periodic table, chemists have separated the entire array of individual elements, each element being made of protons, electrons, and neutral neutrons. Plus, they have discovered isotopes, element flavors in the same place as the other elements, but containing extra neutrons. And finally, ions. Atoms with too many or too few electrons, giving the atom an electric charge. In the next segment, we continue our survey of basic chemistry concepts with compounds and molecules.